Hello, everyone, and thanks for joining today. At this talk, we will focus on MySQL on Kubernetes, and it's a little bit unusual talk for me because my usual state is stands to suggest using database on Kubernetes and encourage people to run. Obviously, when there is a business need, there is not always in place. But in today's talk, I will go through this topic from a little bit different angle. So, considering that Kubernetes became already a standard, like for example, in our organization, we do not consider it as innovation. It's already battle proven way to run, way to deploy databases. But at the same time, there is a perception about some whiteboard story that go containerize your database and the operator will handle everything from failover, scale, YAML change, everything, and you can just go home earlier. So the reality is a little bit different. Day two is different, if to be precise. So in this talk, I would like deliberately not go through troubleshooting runbook, but to make it a decision maker's view. So here is the thing: 6 things that can break at scale. Here is what each one can cost, and it is your call to make a decision and just to be aware. So let's go through, I would say, top 6. And I would start with introducing myself. My name is Obiidykhata. I'm a general manager for Cloud Native at Percona. I'm leading the business strategy DTM for Cloud Native and work across product engineering teams, talk a lot with our open source users, with customers, and mainly focus on making open source databases on Kubernetes enterprise ready. And in technology industry and in open source, I'm for a long time already. You could see me in projects like Alma Linux, Cloud Linux, currently Percona. And today we will go through basically 6 failures, 6 business risks that I would like to cover, and some data behind each problem, and some solutions approach, how to fix it, like some suggestions and things how to view on the problem, and obviously some suggestions on what to do next. But as I mentioned, it's not a troubleshooting runbook. So the whole talk will be kind of split of these 2 columns. What the promise is, what the perception is, and what is the day to bill if you neglect some specific rules of running databases on Kubernetes. So this would be the lens of the whole deck. And every one of these 6 failures coming up as a default that was never meant for a serious estate, for a serious database at scale. And we are here not to bash Kubernetes. We're here to kind of engineer it properly and think what could be done in a better way, let's say. And let's start with the first one, which is not surprising, storage. And I'm starting here because it's one of the most teams get wrong with. So when you run database on Kubernetes, it usually sits on network storage, for example, EBS on AWS and the equivalent elsewhere. And it's a default and it's easy, but it's the first thing our performance team flags is the database slowdown. So the network storage instead of local. And there is two reasons behind that. One, it's sharded. Other workloads sits on the same hardware. That's clear. And the second one, even the premium tier isn't perfectly steady. So AWS and providers similar designs in the best storage to stay within the 10% of what you paid for. So a little wobble is normal by design. And in normal app, you would never notice, but with database cluster, it's different. Every write waits for the slowest node. So if one disk slows down, the whole cluster could slow down. And that's the reality. That's even more common version. And the older default storage, let's say GP2, gives you a bucket of fast performance. And when it runs out, the volume just crawls. So the database is fine for an hour, then suddenly, let's say it hangs, and nothing failed. You just run out of the credits, and always at the worst time when you do not expect it. So here is the thing. One slow node can quietly cost you a fifth of the performance you're paying for, with nothing on the dashboard. So you won't see any alert. Everything would look green for you. And for a regulated workload, that's kind of a dangerous problem. The one problem that you can't spot right away when everything looks fine. So the first one, an obvious suggestion, do not run production on the old default storage. Use provision storage and watch each node separately so you can catch slow disk earlier. And build towards on the long term for your most important databases. Use the storage you control, meaning local or direct attach. That's could come with some kind of trade-off. For example, you get steady performance but lose some easy failover, but it's usually worth it. And the next one would be a networking. And it's one's almost ironic because the very tool that's supposed to keep you up can be the thing that actually takes you down. So the Kubernetes keeps things healthy by checking each piece of replacing anything that looks broken. That's its default normal state. And it's great for a normal app, but with databases, it's not a regular normal app. That difference can bite you. So picture your busiest moment, traffic spikes, it's peaking, and Kubernetes sends the health check basically to ask the database if you're alive. And by default, for example, it could expect an answer within 1 second, and your database at that current moment is busy, so the answer comes back a bit late. And a few of those in a row, and Kubernetes easily can decide that node is dead and just kills it. So the normal traffic spike then just become the node rebuild, right when you have the busiest time. And it's just the beginning. Then it could get worse when that traffic now piles into the remaining nodes, so they also slow down too, and the whole thing can basically just cascade. So there is a thing to remember. 1 second, that just how long by default a database has to answer, are you healthy? Well, it's like under the full load. And that default was written for lightware, stateless apps, not a database doing the real work. So the platform isn't wrong. It just has the wrong defaults. Just in this example, and we see this in some cases. And the business cost of that is kind of the worst kind. So a inflicted outage at peak with a perfectly healthy database underneath it, it's, I assume, not what you would expect. So the suggestion here is pretty easy and straightforward. Give the health check under the load for your databases and size your connection and proxy layer so the database isn't getting choked in the first place. That's usually the easiest trick to perform and think about to prevent such thing. The next one, it would be recovery. The third problem, the third area where we can see the problem, and specifically recovery time. And I would say it is some kind of finance, not even a technical detail. It's number that usually people sign up to, some objective, like often written in the SLA, and you have to report against it. And this number actually matters. So the full, and for example, the full 10 terabyte database, at some of our internal testing, we're always running some benchmarking. So took 16 hours to recover. So 10 terabytes, 16 hours to recover. Against a recovery target that for most critical system is basically what, just 1 hour. And here is the part that basically should bother you the most. The reason was very boring. Almost entire recovery time, 90 with something percentage, was stuck in one single step that just by default was given not enough memory to do its job. So nothing dramatic, just a default that nobody had looked at, and that's exactly why it's dangerous. It's the part of the system you only ever touch in a crisis. And this case perfectly highlights how bad it could be. So in the longer term, the recommendation here is to treat the recovery the same way you basically protect and treating your backups. If you would think about the backup that you would never restore, it's not a backup, it's a hope. The same thing with the recovery. A tested restore is the only thing that proves your recovery time. So be prepared in advance. And let's move forward. The next thing would be area with another type of problems, schema. So in a regulated shop, every change is supposed to be reversible, but schema changes break that by default. So think about the routine change, like adding a column, tweaking the index, that basically can lag the whole cluster while it runs. And once it kicks off, you can't stop it. There is no cancel button. You try to kill it and it just keep going anyway. That's some example of scenario that can go wrong. So there is basically no way out, and it looks every node at once, and you just want it out, however long that takes. So you just wait. And it can get even worse. If one node, for example, one node trips up partway through, and your nodes can end up disagreeing about what the table even looked like. So now you got into the unplanned change you couldn't stop, even in the environment that, by default supposed to be controlled. That's kind of situation exactly backwards. So the reality and the risk is not about technology here. It is about the treating database change as not a big deal. That's the main reasoning we see behind this. And the suggestion here is, once again, treat database change like every other change in the regulated system. What does it mean? It should be planned, reversible, logged, signed off. So it may sound like bureaucracy, but that's exactly what makes the whole thing safe enough to trust it with the most important, which is your data. And let's move forward. Let's not stop here for long. And the next thing would be memory. The fifth problem that could happen. This is basically where the guessing starts to cost you both outages and money. So the old habit from the bare metal days is to give the most of your RAM to the database, and that worked for years. But on Kubernetes, the same move can get your pod killed. And it's not about no backup memory to fall back on, and the limit has to cover more than just the database. It's more than this. It's the proxy, that's the monitoring, that's the replication, all of it basically in the same box, and you have to consider all of this. So for example, if you got 64 gig pod, and the old rule says that give, let's say, 80% to the database. So that would be 51 gigs, and that leaves 13 for everything else. And if you're using group replication, that needs about 10% more memory again. So you can go over the limit, the same system just kills the pod. So the natural reaction is to play safe and to give every database extra room. So it is fine for one case, for one database, but what to do across hundreds of databases? And you basically would start paying for memory nobody uses. So the guessing costs you both. Guess too high, you can get the outages. Play safe and you just waste money. And this is exactly the opposite why you probably came to open source and run databases on Kubernetes at the first place. So the suggestion, pretty straightforward. Stop guessing. Size it from your real numbers and count everything sharing the pod, not just the database. And there is a free tools for that. I'll share with you some ideas later that can do basically all the math for you, the open source. And in the long term, basically your goal, the main idea is to make right sizing automatic. Every time you deploy, instead of someone guessing, you should have all your settings and sizing already set up exactly with the operator help. And the last but not least would be scaling. So the last problem, and basically this one just a fact you have to plan around, and the platform won't fix it for you in any way. It's kind of easy to think that Kubernetes make a database endlessly scalable, but it's not exactly correct for all cases. So a rational database scales reads fine, one writer, lots of readers, same as on a bare metal, but it doesn't scale writes. And Kubernetes alone won't change that. So the only way to scale writes is to split the data up, basically to shard. And we also will get to that. So the bigger database gets, the longer it takes to rebuild it and to recover. That means the longer outages and more of the disaster recovery risks. So your long-term strategy here should be to replace that one big fragile database with the several right-size one. And that used to be expensive when it was with the cost per instance, but now with open source, with Kubernetes, it is pretty affordable. when you've been charged just for resources. So plan the whole things and then do it by stages, with the least important first. But yeah, the main idea is to keep it the right sizing, not to pile everything into one instance. And looking at our timing, we still have some time to sum it all up here. So yes, let me kind of pull this all together for you. So if you will look down in the middle column, every one of these has a real business cost. So storage can quietly eat your performance, for example, and networking can cause some outages. That's a real problems. And if to look on the right column and notice the fixes for all of this, they're all of kind of same kind move. For example, own your storage, own your settings, practice and budget for recovery, make changes safe and logged, size on real numbers, right size and shard. So underneath of all of the six is really one course. Default bit for small data. And basically one answer: do it deliberately and own it. And that owning it and doing it properly is exactly what open source and the operator will help you with, will let you do. But the strategy should be in place. Those tools will help you to execute, but the planning should be in place. And talking about the tools that could help you with some risks mitigation, I would like to mention and highlight a nice new open source tool, MySQL Operator Calculator for Kubernetes. It's basically a free open source tool from one of Percona expert, Marco Tusa. If you will give it your real pod resources and workload type, it will return a mathematically safe configurations for how to configure your sizing. So I would encourage and suggest you to try it. Here is a GitHub repository where you can take a look and also find a live demo of it. And another thing, obviously, is Kubernetes operators. And fortunately, I'm working with a company that that works with one of the most successful tools, orchestrator for MySQL on Kubernetes, is Percona operator for Kubernetes based on PXC. And this is the Galera one, versus we also have the group replication operator. So both were running, both open source, and we don't force a choice. So we cover the whole MySQL, we try to cover the whole MySQL surface, so you can pick whatever you want, what is comfortable for you. And here is some differentiators. But yeah, my suggestion would be to go to docspercona.com/Percona operators, where you can check both tools, easily download and set up. And me and my team always ready to help with installation, running, and any problem you are facing. We're quite open. If you'll take a look on our public roadmap, pull requests, comments, it's always with the quite prompt responses. So yeah, this is definitely something worth to check if you consider to run MySQL on Kubernetes. Those three tools that I'm personally suggesting. And a final thing that I want to close my presentation with is Basically, the phrasing about default configs are for small data, and my presentation proves that scale is the business decision you engineer. So all of those risks basically piles up and increasing with with the amount of data, with the number of databases, number of pods, instances, etc. And this is your decision how to make it right from the beginning, or get some help with that. But basically, yes, my suggestion would be try calculator, size it right at the beginning, explore the operator to automate it also from the beginning, and keep it under control. So that was it. I will be glad to answer any questions you have. Send them in a chat. And yes, thank you very much for your time, your attention, and yeah, have a good time of the day that you have there. Thank you and bye.